So Tyler and I's project was a weather model, and we chose multiple different models for comparison for the city of New Haven and the state of Connecticut. So a quick overview, we are predicting three weather variables: average temperature, precipitation, wind speed, and our data set is monthly weather history from Tweed National Airport, and our modeling approach is to train separate models for each month, and then evaluate and compare linear regression, support vector regression, and random forest regression to try to see which model is the best and provides the most accurate data. And we're going to provide predictions through an interactive tool for the user. The importance of weather modeling. The importance of weather modeling is for long-term weather trend estimations, which are impactful in terms of climate monitoring, city planning, agriculture planning, and disaster planning, infrastructure planning, and also natural disaster planning. And why these models are important is that the specific models detect patterns that humans struggle to see and that might be underlying issues that these humans can't see. And forecasting by year, not by the day, reveals a large-scale climate shifts. And getting into our data specifics, the weather station used to train models it's right there. It's located in New Haven, Connecticut, Tweed Airport, and the data recorded was the monthly average temperature, the monthly average precipitation, and the monthly average wind speed. Our data set um, was the monthly average weather observations. The columns used were date, extracted year and month, the temperature average, precipitation average, and the average wind speed. And the data spans multiple decades, and the model's trained only on non-missing values. Each month receives its own three regression models. And the models specifically chosen were mentioned before, but they're the linear regression model, support vector regression model, random forest regression model. And diving into the linear regression, why we chose that, it is suitable because the data set exhibited somewhat linear trend, temperature trend, and it produces easily interpretable coefficients, meaning the slope and the intercept. And it serves as a good baseline model to see how the data transpires over time. And this is also some fast training and low computational costs. So it kickstarted the project, and we were able to see small trends and then move on to the more complex regression models to try to figure out these deep underlying patterns. And some of the limitations with this model is that it does not capture complex seasonal or nonlinear effects, which is why we dove into the support vector regression because it captures nonlinear patterns and it handles noise slightly better than linear regression and it produces smooth prediction curves, which is useful for weather trends. And it is a flexible model that balances both bias and variance. And some limitations with this is that it's computationally expensive on large data sets. And the main model that we used was the random forest regression. And this is a collection of decision trees, and it captures nonlinear interactions and month-specific patterns. And it is very robust to noise and missing values, and it provides importance insights. But some of the limitations are that it's less smooth for some certain predictions, and it can overfit without fine tuning.
Uh, some specifics of our models. The data is split per month, and this data is taken from 1948 to present day. Um, we trained each model on each month, so we have a model trained for January through December for each of the three models. Um, and we store these models with a key shown there. We predict by the user entry of a month and a year. And that will output the as seen in the demo coming up, the average temperature, precipitation, and wind speed for each of the three models. And we also have graphs comparing the three models across the years, how it predicts versus the actual real data. Here's a quick screenshot of our data. We have an entire spreadsheet showing how well each of the models reacted to the or trained off of the official data. Here is the here is the spreadsheet of that. Um, so the data is split into training data, testing data, and prediction data. Um, to for each of these, the months chosen were January, April, um, July, and October because these are 4 months that span equal distance across each year. So we get a nice view of the seasons. Um, we can see that each of the linear support vector and random forest regression models were trained for each month. And for the training data, we have four different years: 1949, 1976, 2002, and 2024, with the 4 months in each, comparing the predicted and actual data types. On the right side, we have the MSEs of how each of these models performed, with the random forest regression model performing the greatest, having the least MSE. If we scroll down a little, then we can see here's the testing data. The testing data is very hard to do because the model is trained off of as much data as we can get. Um, and that includes 2024, meaning 2025 is what we have to work with, which is not too much. Um, and Below that is the prediction data. The prediction data includes years which are far away but kind of near, and super far away to test how our models would react. So we have the 1800, the year 1800. We have the year 150. And you can notice some trends, especially with the linear regression models. And then we have the year 2100, and then below that, the year 4000. Some limitations. Uh, some data was missing within our data set that we chose from the Tweed airport. The average wind speed, for example, was not recorded at the airport until 2001, and there is just a bunch of missing data from 1977 to 2000. Uh, Another limitation, the model outside of New Haven, the weather may be different, so the model may be inaccurate for places outside of New Haven. The amount of data recorded, we can't get data from the 1800s because the Tweed Airport did not record data back to the 1800s, even the really early 1900s. And there's a lack of testing data, as I previously mentioned. It's kind of hard to get testing data unless you wait some time, due to you don't know the weather of the future precisely until it happens. And yeah,
And getting
uh,
into, you got this one, Tyler.
okay, okay. Uh, So yeah, to compare, this was previously touched on in the Excel spreadsheet, but we have the MSEs on the right, but we also have the graph on the left now, comparing how the three models react to each other. With the blue line being the actual data, we can see that the random forest regression matches that data. The ups and downs are small trends that we see, and we have the yellow is the linear regression, the green is the SVR, and the red is the random forest regression. And to conclude, we see some trends with our metrics. The average temperature, for example, will grow over time. Um, this is shown with the linear regression. Uh, when we do the super early one in the year 150, all the way up to the year 4000, we see an increase in temperature. Average precipitation seems to increase over time, except for the winter, and the winter decreases over time. The average wind speed decreases over time, except in the fall, where it's seen to increase over time. And we concluded that the random forest regression tends to be the most accurate.
Now to get into a quick prediction demo, looking at our code base. Um, So right here is the graph. The user gets to see the graphs by months. And in here, you can also see it looks like the random forest regression model seems to slightly almost overfit, but that is actually slightly better for temperature readings because it's very, you can see it's all over the place. So almost an overfitting kind of fits better for the crazy nature of the data set to try to keep it more properly aligned as opposed to a linear regression model where over time we saw that the temperature severely decreased, and then in the future it severely increases. And then right here, the user can select the month and the year. So right here we have a prediction for month 6 in the year 20, and it gives you the temperature average, the precipitation averages, and the average wind speed. And then for the final combined prediction, what we chose for that was the random forest. That's what's outputted for the user to see, and that because it is the most accurate that we have seen. And thank you for listening to our presentation.